All right, so I'm going to hand back to our final speaker who's going to introduce himself, basically. But this has been great, and we want to give a big thank you to Quickwit again for taking over our platform. Francois.
Thank you, Raleigh. So now I will talk about the architecture of Quickwit and how we build an efficient search engine for logs. So it's definitely totally different from typo-tolerant or user-facing search, as you may have seen in Harrison's presentation. But first, I will just say a word on me. So I'm Francois. I'm a node engineer with 10 years experience in mostly in Python. It was a great time, but then I co-founded Quickwit, and 3 months later I fell in love in Rust with Rust. It's just like now when I push something into production, I'm not scared. So that's a really nice feeling. So let's back to the presentation. Search engine for logs. First, let's define a search engine. I'm very glad that Harrison told about TonTV and things, but let me just tell that a search engine is simply an engine that is building an inverting index. An inverting index, what is it? It's just a dictionary of every word that you have among your documents. And for every word, the engine will build the sorted list of document ID. And that's all. And that's on the indexing part. And then on the query part, when a user query comes in, the search engine will just read this inverting index for each, and will read the list of document ID for each word inside the query, the user query, and will process and intersect all the document IDs and will return them the result. And that's all. Just an additional comment about this diagram. What is happening in general is that you have one indexing process that is ingesting the documents that are coming, and then you have one query process that is processing the incoming queries. The indexing process is working by batch. So when you commit, it will flush the inverted index on the disk. And then when you can continue to ingest new documents, and it will, when on commit, it will generate a second inverted index file. So for TonTV, it's not only a file, you have several files, and I will show you this after later. And then on the query, you will be able to process the query on each inverted index file. If you want to have more information about that, you can have a look at a very interesting Algolia blog post at the Quickwit blogs and Fulmicoton, which is the creator of TonTV. So now that we know what a search engine is, we can have a look at the characteristics of log search. The first one is the volumes of logs that you have to handle versus the very few queries that you have to handle. If you compare it to an e-commerce website, you will have probably 10 millions of documents, and you will have to handle like 100 queries per second. But if you have, if you need to handle logs, it's perfectly normal to have 100 terabytes of logs, and then only one guy in the company that will make like 3 queries per day to search for a bug, for example. So it's totally different. We can derive some, one thing about that is that for an e-commerce website, your CPU usage will be spent on query processing, and most of your CPU will be spent on query processing. And for a log search engine, most of your CPU will be spent on indexing. So in this case, you may want to have different machines for indexing and for searching, for example. The second characteristic is that it's immutable. In general, you don't want to update logs. The third point is that in general, you don't need to score. You just filter the logs that you want. So if you want to search a bug, and you would just want to sort the logs, the match logs by timestamp, for example. It's also cost sensitive, especially compared to e-commerce website. So when you have an e-commerce website, you are not very interested by lowering the cost of your search engine. For example, it's okay if you have one machine that is running with a 10% CPU, that's okay because it's driving so much revenue so that you're okay to spend a little bit of hardware on this. But for search, if you can drop like half of your cluster on your 100 terabytes, you're very happy if the query is taking 1 second, for example. So in general, you're very happy when your costs go down. And last but not least, the log search characteristics is the last log search characteristics is the multi-index, multi-tenant. In general, in your cluster, you will have to handle logs coming from several tenants, and so you will need to handle them to ingest them in different index, and your search engine you have to be performant on all your tenants. So now we know what a search engine is, we know what a log search engine is, the characteristics at least, and I will present to you now the typical architecture that exists since the 80s for search engine is the shared nothing architecture. It's an architecture that is very simple. Imagine you have a big data set, you split it by shard, and then you say that each node will handle this shard. There is no shared memory, there is no shared storage. So each node is in charge of a subset of the data and and does not depend on the other machines. If you want durability, you will of course need to add replica. This architecture is used by Elasticsearch, but also by Cassandra, Mongo, and many other databases. And it's a very good architecture, of course. Let's have a look at what a search engine, how a search engine works with this typical architecture. On the search part, you start with a query. Then what we call at Quickwit the root node. This is the first node that will receive the query, the user query. This query will then distribute the workload over the different leaf node. So it just acts as a coordinator. So you can see that the query will be sent to each shard. So it can be a replica, or it can be the primary shard. And then once the root node has received all the results from the leaves, it will then merge the results and return the results to the user. And that's all. The interesting thing here is that you have different moving parts here, the query, the results, and there is one thing that is not moving is the shard. So one of the principles of shared nothing architecture is that you move the small things, and that's great because you don't want to move huge chunk of data. Okay, so next, let's see how the indexing is working on this architecture. So generally, the user is sending some documents to an ingest API or push API, and then the cluster will use a routing algorithm. Typically, you will take a hash on the ID, and that will determine the shard ID, and then you will send the document to the right shard, and in general, you will have a leader in your cluster that will also take care about sending the document to a replica so that you are safe, you won't lose any documents during this phase. And I think I'm okay on this. So one remark this, if you are using Elasticsearch, for example, you are doing the indexing twice. If you have two replica, so one primary, two replica, you are indexing 3 times your document. So one on the primary and two on the replica for the two replica. And this is not a problem for an e-commerce website because indexing is a small part of your cost. But for a log search engine, as your CPU is spent almost only on indexing, then it's like not negligible at all. So this can be a source of cost efficiency here. I think I want to say something else, but I will say it later. So this architecture is really great, but it can come with some drawbacks. So I will quote the Datadog engineers that wrote an article 2 weeks ago presenting their new search engine that does not use the shared nothing architecture, but a shared disk. So I will show you that later, just after. And so that one of the drawbacks they pointed is that in a multi-cluster environment, you can have a problem when, for example, one tenant is aggressively making queries, and it will have an impact on other tenants. If we look at this diagram, you will see that in one shard you can mix several tenants, and if one tenant is aggressively making query on this shard, you will have some issue. It will have an impact on other tenants. So in a shared disk architecture, in a shared nothing architecture, sorry, it's hard to isolate the behavior of each tenant. So this is one drawback. And for the Datadog, it can make the entire cluster unavailable. So in this case, it's even worse. There is also one interesting remark from Snowflake engineers. So in their papers, when they presented their architecture, so they also use a shared disk architecture. It's different from the shared nothing. So you share basically the disk, the storage, and they identified like some scenarios where it is not desirable to have a shared nothing architecture. So for example, if you have heterogeneous workload, for example, if you want to bulk insert massive amounts of data and you don't want to search at all, so you want to focus on the indexing, then you also have the membership changes. So for example, if you have some node failures, you will need to add new nodes. And in this case, you need to move the data. At least you need to copy the shard data to, and this can be very long to take. And this is one of the drawback, of course, that you can have. So a little summary of the pros and cons of a shared nothing architecture. The data does not move, so this is very good, at least when everything goes well. You benefit from low latency. I did not explain a lot about that, but when you collocate your data and your CPU, you have a low latency. So in general, it's pretty good at this. You have also a low time to search. Time to search is the difference between the time when you insert a document and the time you are able to search your document. So it's the commit phase that you saw in the previous presentation. And then there is also the mutability. So the mutability, we don't need it for logs. The low latency, it's okay to be a little bit slow on logs, so that's okay. Low time to search, we can discuss about that. And there is the data which does not move, which is a really good strength. But guess what? Since the 80s, the network bandwidth has increased a lot. And today, when you start a new server on Amazon, you will at least benefit from a 10 gigabit per second bandwidth. So that's huge. And so once you know that, you may think that we can change the architecture. And so spoiler, we are doing shared disk architecture for search, and I will explain you how we did that because it comes with some issues. Let's first present you the shared disk architecture of Quickwit. So first thing, if you look at the indexing part, you have one indexing node that will take documents from a distributed queue. And behind the scene, we are using TenTV, and we will commit. We will use the commit function from TenTV. This will build the inverted index. We put everything into a file called a split. So it's a small piece of index in Quickwit. We upload it to a shared storage called, for example, Amazon S3, can be HDFS or MinIO, whatever. And then we also update the metastore. So here, one of the important things is that for durability or to be sure to not lose document, we are using the distributed queue here. So we ensure by taking some documents from Kafka and by then pushing the inverted index to the shared storage, we can ensure that in case when there is an issue on the indexing node, that at restart we can still restart from the right offset in Kafka. So we store small things in the metastore, typically the offset of your Kafka queue. And so this is very nice because we have isolated the indexing part. And then on the search part, when a user query comes in, you have the same mechanism as for the shared nothing architecture. You have the root node that will then distribute the query on the leaves, and each leaf here will have no data on the disk, and it will need to fetch the data from the shared storage. So one nice thing here is that we have separated indexing and search, so we can be more efficient in terms of CPU, because we can have dedicated machines for indexing and dedicated machines for search. Then on the indexing part, we index only one time a document. So instead of 2 or instead of 3, we index it only one time. So it's better. And then we benefit from a cheap storage. So generally, we are using Amazon S3. All the metadata of our index is saved in what we call a metastore. Today we have one implementation that is using PostgreSQL behind the scene. And the good thing with that is that finally all the critical data from Quickwit is handled by borrowing technologies, so that everyone can sleep at night. So you won't lose your data on Amazon S3. It's replicated on several regions, so you can sleep. And finally, on the search part, I did not give you details about that, but when you receive a query, you have no data, so your nodes are stateless. The fact that your node is stateless is super cool because you can start a new node or stop as you go. So it's just a matter of 1 second, and then you are ready to receive a query and then fetch data from the object storage. This is particularly cool when you're in a multi-tenant environment. So that's the idea. But now we need to solve 3 problems. Being sure that we can stay truly stateless without having a latency of 1 minute. Then we have a lacking throughput because, as you will see, Amazon S3 is a very bad is equivalent to a very bad spinning disk. And then you have also latency, so same problem here. It's not an SSD, so when you make a request on Amazon S3, you have a penalty of 70 milliseconds. So let's start by solving the first problem. So to stay truly stateless, we need to solve this problem of opening an index. When you open an index on TonTV, it means reading a bunch of header and footers of each files that are making your index. So in the case of TonTV, so as we are using TonTV, a split is just a TonTV segment, so it's a piece of index. You have a bunch of files in it, like the meta-JSON describing the schema. You have the term dictionary, the position, the store where we have all the documents that we want to store. So the problem is that when we open this index, we are making 28 reads and we read only a small amount of data. And this is a problem because it is not a parallel. These reads are not parallel. We can start with a header, and then we will look at the footer, and then we will read another header from another file. So 28 reads with a 70 millisecond penalty for each read is really bad. So what we did is we decided to concatenate all the TonTV segment files and add what we call the turbo cache at the end. And this turbo cache contains all this metadata, the header, footer, and that we need to open an index. So now to open an index, we only need to download, to fetch the read part, and we are ready to receive a request. And that's also here. At the beginning, we had 28 reads, and now we have only one. So, okay, it's 70 milliseconds, but one read, so that's okay. Problem 2 is the bad throughput. So if you want to search terabyte with a bad throughput, it's not a great thing, of course. So just to give you some figures, Amazon S3 is down. It's like 100 megabytes per second and with 70 milliseconds of latency. And usually when you're working with Elasticsearch or any search engine, you want to use some SSD, so EC2 attached SSD, so you can expect like one gigabyte per second of throughput and 1 millisecond of latency. But S3, with S3, you can parallelize requests. So if you manage to parallelize all your requests that you're making to your index, then you can have a great throughput. And we did that. We tested it on some. So you need to choose wisely your instances on Amazon and choose the ones that have a good bandwidth with object storage. But it works well. We achieved like one gigabyte per second of throughput. So what we did for that is that we looked at all the pieces of data that we want to fetch in a TonTV inverted index. And we needed to plan our IO ahead. For example, if you have 10 words, you need to say, okay, I will need these 10 term dictionary parts and then this 10 document ID list and etc. And so we are making this so in Quickwit code so that we know exactly which piece of data we need, and we run them. We run the query, the request in parallel. The last thing to be performant is to avoid the random seeks. So we started with the hot cache. But we also, but for Quickwit uses, for Quickwit purpose, we also change a bit the data structure of the term dictionary. So usually the term dictionary, it's a try. It's a try intensive, but we change it to an SS table, so to be able to fetch data not randomly and and reduce the number of random seek. So in the end, we achieved when we receive a query, we only need 3 random seeks to know which documents are matching, and then we make an additional seek for fetching documents in the doc store if you want to retrieve also the documents content. A final word on our Rust stack. Just to say which crates that we are heavily using. Of course, we are heavily using Tantivy. We have developed also an actor framework, so don't hesitate to have a look at it. It's really interesting for the indexing pipelines. So we need to do lots of things, like we need first to index, then save it on the disk, then upload it to S3, then publish the metadata on the metastore. So we have these different steps, and to coordinate all of that, it's very nice to have an actor framework. So we implemented it in Quickwit. We of course we are using, of course, Tokyo asynchronous runtime. Tokyo tracing is very nice also to understand how the tracing are distributed. So for distributed tracing, it works perfectly well. So for debugging purpose, it's awesome. For the communication between nodes, we are using Tonic, chit chat that Evans presented you at the beginning, Warp for our REST API, and many more that I won't quote. But I'm really happy to be able to use all these fantastic tools that the community is developing. So really happy to code in Rust. Have you got any question?
Thank you very much.
Yeah, can you say a bit more about what goes into the metastore?
Okay. So the important thing about the metastore, for example, for an index is to know which splits are in your index. So at least you need the split ID, then you need to know where your split is stored. So you will have the URI of your split. So for example, the split is in a given bucket, and then we store also the some file offsets to be able to fetch the turbo cache. And we also store the index configuration, like the schema of your split. And that's pretty much all. It's very small currently, and we want to keep it small anyway.
And just to follow up, do you do the recompaction, kind of like the Husky blog article? Do you have to recreate those
So
splits?
compaction. So what we are doing currently is merge. So I did not talk about that, but when you index, you will produce splits. Generally, the splits are not as many big as you want. Typically, for logs, we expect to have splits of 10 millions of documents. And so what will happen is that your indexing node will produce several splits of 1 million documents. And when you have like 10 splits with 1 million document each, it will merge them. So currently it's the indexer node that is doing all this merge stuff. And we are caching the split to avoid to fetch splits from the storage. So we keep everything on it.
Thank you.
Thanks. Thanks for the presentation. So what are the cost savings? How much cheaper do you expect Quickwit to be than sort of comparable log search offerings?
Okay. So if you compare to Elasticsearch, we expect to be 10 times cheaper on large data set. For very small data set, I expect less than that. So that's what we currently expect. At least it's at least. I'm conservative when I'm saying 10 times cheaper.
When you say large data set, what's the size? How many terabytes are we talking?
Terabytes,
Tens, hundreds?
tens terabytes typically.
About on the indexing part, well, it's gonna be complex. How do you handle the the partitioning there, the splitting? Like, yeah,
So we don't have partitions. What's happening is and it works quite well for logs. So that's and I can complete my answer to Jack's question. We are storing also the timestamps. Typically, the logs that you will send to Quickwit will have a timestamps. And so what will happen is that for each split, we will store in the metastore the first the start timestamp and the last timestamp. So what will happen is that when you have a query and generally your query will have some time range and constraints, we will be able to split to prune splits and target only the relevant split. So it can reduce dramatically the number of splits that you will ask. Um, so it's a kind of sharding, but we don't need sharding here because we are on shared storage. We also have another mechanism for pruning. It's called tagging. So you can choose one field, and if how can I say that? If a number of unique values is not the cardinality is not too high, you can then store the tags on the metastore, and then you will be able to prune split very efficiently.
All right, last question. One more question.
I just wanted to ask a question about the actor model. You've implemented your own. When looking at Actix, I assume this works purely on the same program, on the same process, not over the network. Is this a design decision that I assume all this is across the network? And also with the Evans's talk on chit chat, was this all a part of that architecture? Yes.
Okay. For the moment, we use the actor framework not for discussion over the network. It's only on one indexing node. It's only used for handling the indexing pipelines. So you have a bunch of actors, and then you have a supervisor actor that will restart if there is an issue, for example. And that's all. We plan to use our actor system over the network. So we want to do that, but it's not used in chitchat, for example. It's only used for the months on the indexing pipeline, and it only works today on one node. So that's all.
And if that's the case, then why would Actix not be the choice that you wanted to go with?
That's a good question, and I think I cannot answer you because I'm not the guy who made this choice, and I can't remember. I don't
No
know.
problem. I'll take a look. Thanks.
it's about where you guys are placing yourself in the market. Do you plan to compete with somebody like a company like Splunk, or where do you?
Yes, that's a good question. For them, as of today, the hard thing with to compete, it's hard to compete for us with Splunk because you have many functionalities, many features related to security stuff. So at short term, I bet we can be used by companies that are providing some more advanced features, and we can replace their backend with a Quickwit. And and at short term, we are targeting simpler use cases. Like you have a low-kick use case where you have a Grafana and you just want to search through your logs, And our target now is to be compatible with Grafana, and so that people can easily change their backend, use Quickwit to store their logs, use Quickwit to store their traces. So that's our plan. We are not ready for the current release. We are releasing tomorrow the 0.3. We are almost ready for this kind of use case, so it will come in a couple of months. But it's really basic observability use case on logs and traces too. We should be able to do the same for traces.
Thank you very much. Want to give Francois the last word from Quickwit. So please share details, share any job posts that you have, share anything else that you want to share to the London community.
Okay. First, thank you very much again for inviting us at this meetup. Thank you for your attention. It was a bit long, I guess. And so today we are a very young startup, and so we are obviously always interested by use cases where you have to handle terabytes of data and you want to search on it. We can be interested in use case that are not especially for logs. So don't hesitate to come to us, to come on our Discord server and chat with us. We will be very happy to give you some advice about how to do your search. I promise we will not sell our product if it's not relevant for you. And last thing, we are recruiting currently a senior software engineer. So please apply if you're interested, or talk about it to your friends. And I guess we also have an internship open position. So the same, you can apply, and we will answer you.
Amazing. Thank you very much. Give a hand, please.